Hi everyone, this is Tom speaking and welcome to our digital signal processing class. The first topic of this semester is about classification of discrete time signals and systems. But before talking about the actual contents of this chapter, I want to give a few updates about this course. So this is some kind of introductory video. A well, in this series of video, we're going to talk about the classification of digital systems and the classification of digital filters. So basically, we're talking about a reminder of what was taught last semester in the signals and systems class with an update for digital world. Okay, so just before starters, I remind you that my email is there. Okay, please use it cautiously. And for the moment, I still don't know what is my fully uh, weekly hours, so any receptions hours should be set up with me by mail, and office hours will be published in the syllabus any week now. So what's going to be in this class, in this course? I mean, it's a very modest introduction to digital signal processing because this is a very, very wide domain. Okay, so chances are that people interested in signal processing will continue studying this part in their master's degree. So we're gonna talk about the basic tools of digital signal processing. I mean the Z transform, the DTFT. FFT is not a transform per se, it's rather a fast implementation of another Fourier transform, which is the DFT. We're going to talk about subsampling and oversampling. And I will present at the end of this semester several applications, mostly designing finite impulse response filters for biomedical applications and stuff. So what I want to emphasize this semester specifically is what do I need to know? Okay, first you need to know English. Okay, this goes without saying, but considering that I'm a French lecturer teaching in English, people whose mother tongue is in Hebrew, this part is kind of, mandatory. A good understanding of complex numbers wouldn't, wouldn't damage. And obviously, since this course relies a lot, on what was developed in signals and systems, then please go back to signals and system material. And the rest of mathematical course tools I will define later. So that's it. At this stage, if this was a live lecture, I would ask you if you have any questions, but considering this is a video, you don't have any, or maybe you have and you cannot ask them now. And actually, yeah, that's fine by me because you will ask questions during the lectures itself, and I will answer them. Okay. So what is digital signal processing? Well, as of today, we're living in a digital world, so it means that even if I'm a part of an electrical engineering department, so I have to know some electronics, but most of my image and signal processing tasks, I'm doing that in front of my computer. And for example, or let's say that a basic signal processing chain or pipeline would be more exact, would be like this. Okay, you've got this kind of analog phenomenon. By that I mean it could be either some music that you're recording, or some kind of electromagnetic wave, or some kind of electrical voltage that you measure. That's really okay. So at this step we're talking about some kind of continuous time signal, something like this. And this continuous time signal goes into an analog to digital converter, which will basically consist in sampling the signal and normalizing the time scale, so that now instead of having the original signal, then you have a sequence of numbers. Okay, so considering that the time scale is normalized, this is not exactly a sample version of xt, but it includes inside an array all the values one after the other. Etc. Okay, and this part is a digital signal. So here, this is where DSP world starts. To be quite honest, it starts a little bit before, because the part which is related also to A to D transformation is somehow related to digital processing. But starting this point, I can do anything I want. I can remove noises, I can extract features from XN, etc. So the most important part of this course is related to this part of the pipeline. And obviously, if you need, for some reason, to listen to the music you recorded, then you can put this YN into a digital to analog converter, and then you have this. Okay, but most of the class will be dedicated to what happens between the analog to digital converter and between the digital to analog converter, obviously. Okay, here in this video I'm voluntarily not talking about what's happening in sampling, or does the input signal, the continuous time signal, verifies like Nyquist condition. Okay, but obviously this is something that is important. So one of the most important assumptions that we will do along this whole semester is that a xt, the initial analog signal, was band limited, and that the frequency used into the analog to digital converter is sufficiently high. It means that all the frequency content which is above the Nyquist frequency will be either lost, either distorted, okay, and we have to take that for granted. All right, so this is more or less everything I wanted to talk about in this very introductory video. So we're gonna talk about the rest of the chapter in the next videos, and I will try to organize them along the way. Thanks for watching, and if you have any questions, please remember that I will answer all these questions during the lecture. Bye.